various things go, various things start up. I'm using a thing called Jack. It's very good for plugging the sound software together. If you've done anything with using Linux, you'll know about Jack. Now let's start making ignore that error message I have. And the server has started in the background, which is running a little network of components for this visual programming language written in Java.
By you, Jim?
By me, yes.
How many programming languages have you written now?
6 or 7. Right. I'm creating a new library of patches, which are bunches of components wired together. So, if I create a patch, I've got to connect to server there. It's a client server thing. There's a server in the background, also written by me, doing all the work. So we have a little bunch of outputs. And I want to play a chord. So I select a chord component. The parameters for which, well, who in here has done stuff with music and knows a little bit about music theory? Plays musical instruments a bit, yeah, okay. So the chord will just take, it's a bunch of notes it picks from a scale. And in this case, I'm going to say the major chord, and the notes it's going to pick are the first, the third, and the fifth. So that's going to be your actual major chord. I say 0, 2, and 4 in the box there because I have a program, and if I start counting to 0, you're not hearing anything, of course you won't, because I'm not playing anything yet. So I need a note picker, note player rather, there we go. Wire that to the chord, and then I need a thing to say what notes I'm going to pick out from the chord to play. So I'm going to use a denary sequencer component, which I will wire up the number outputs and the trigger outputs accordingly. I think no, that's not right. Those two. Sorry, this. And then I'll have a little clock ticking away, making trigger events. That's a clock divider, I haven't done those yet. So, a clock. Going into the sequencer, and playing the notes. Boring. So what I'll do is I'll make the sequence a little bit more interesting. And then what I'll do is I'll start to do some maths with the numbers that are coming out of the sequencer. So I'll add another sequence. Which is shorter. In fact, it's just 0, 0, 1, 0, 0, 1, 0, 0, 1 over again. Ticked by the same clock. Adds the two together. And that's what I'm going to say. It has never crashed before. I mean that. Back in time. I thank you all for your forbearance, and we'll now do just a standard demo. If the thing ever wakes up. Yeah. It has never crashed before, genuinely. It's really never crashed before. Oh, load demo, man. Right, I'm going to go back to the window. Oh my idiot. I'm not going to reboot. What on earth? That's a bit natural, isn't it? I'll put things up. Always practical job. Now you're like. Oh, All right, someone else can talk. If I have any time left later, I may come back.
Cool, cool. Thank you, Jim. I have a sailboat. I have a sailboat in the house.
Where's that?
They're over there. I'm staying at the wrong bit. Come on. I don't need to stay on video. I've got it because you can do it. This is how the sailboat. Give me your stickers. Where's your maps?
We're at the sailboat, as you can see. So this is us at the end of Portugal. So now we're only 3 students. We used to have a lot more. They've all graduated or gone on likewise. So we're a student team, and we're all students. We want more to join, so if anybody's interested in joining us at the end of this, speak to us. So what do? We build autonomous sailboats. They're autonomous and remote controlled. And we compete in competitions. The boats, we've got 2 main boats running at the minute. One's called Dewey and one's called Kitty. Dewey is a maxi loop, so designed by one of the visiting lecturers. There's a cat rig, a bigger boat than Dewey. So the competitions that we've done this summer was Sailbot and WRC. So Sailbot is a competition in the Americas. So this year it was in Canada, and we came third. There's 4 competitions, 4 events in the competition. So there's a fleet race, station keeping, payload challenge, and a long distance race. So a fleet race is where all the boats are in the water at once and they race each other. The station keeping challenge is a challenge to stay in a box for a set amount of time. So you can stay in one place. The payload challenge was to see how many bricks you could get in your boat without it sinking and still sail it. So we managed to actually get 22 kilograms worth of bricks in our boat. And it immediately went into the other submarine, it didn't, so it was fine. And then the long distance is a big long course that's longer than the fleet race, and you have to see if you can do it. A bit of an endurance test. The next competition we went to was WRC, so the World Robotic Sailing Championships. And that was in Portugal not long ago. Again, we came third. And there was the fleet race, virtual anchoring, area scanning, and a vision challenge. So again, the fleet race is the same thing. The boats in the water all racing at the same time, so you can come first. Virtual anchoring is similar to station keeping, where you have to try and stay in one place. But it's judged in a different way, so it's called a different name. Area scanning is to scan a big area and see if you can get into all the boxes. So that would have a scientific application in the real world to scan an area and see what's happening in that area. And then there was a vision challenge. We didn't really compete in that. We tried to, but we kind of botched it at the last minute and it didn't really work, so we didn't. So that would be to go up and down a strip and avoid a big obstacle that will come in at some random undefined point. and yeah.
So as far as software is concerned, everything that we've got more or less is running on the Raspberry Pi. We've got an Arduino in there to basically do the communication between the to read from the sensors and to write to the servers and such. But otherwise, we've got this thing which was thought up by Louis, who's left now, which is called BoatD. That's the robotic sailing boat Demon, which is kind of running in the background. And is sort of a nice big control-y thing for sailing boats. And then we've got the behaviors which are completely separate. So you run a behavior into BoatD, and then BoatD then sends those out to the Arduino to control the servos. And yeah, BoatD's got sort of functions like got great gray circle calculations and stuff, so we don't have to do that in all our behavior calculations. And then as far as behavior, this year we were working on how we were going to go upwind. So if anybody doesn't sail, you can't sail into the wind. So you've got to kind of go as close as you can without going directly up. So you've got to do this kind of zigzag. So we set a 15-degree angle between directly upwind and the edge there, as you can see on the triangle. So we were measuring the angles, and once we got beyond 15, then we would tack and head in the other direction. So SailsD was a sailing simulator, which was again written by Louis, because most of the things were written in C, and it basically simulates all the physics. So BoatD is, you're able to run BoatD either on the real boat, or you can also run it straight into SailsD. So you'll have the same sort of situation. You'll have it returning the kind of what the sensors would read from the boat, and then it allowed us to test everything. It was quite useful because when we were working on particularly the beating algorithm, we weren't able to just put the boat in the water every time. It was difficult to see, so we were able to just run it through SailsD, and yeah, it was a good way to visualize everything. And then our telemetry. So we've got 2 XPs. There's one inside the boat, and there was one on my laptop, and then we were using APM Planner. So it was using the Mavlink protocol to send the location. And it was also, in theory, being able to send from the laptop to the boat coordinates for a different course, which sort of worked occasionally, but also didn't. And then, yeah. And then we forgot the XP when we were going to Portugal, so we weren't able to use it, but it was fine. So. And then on the electronic side, this year we were working on, so before we had quite a mess of tangled cables inside the boat. So this year one of the big projects was to build a PCB for Dewi, which is what you can see there. So that was designed by Will primarily, who is at the moment doing his industrial year. Yeah, and it works, except for the fact that I blew up a GPS and we had to replace it, but that was fine. Otherwise, it's all right. And then transport, that was another thing. Previously, we'd been transporting it in this broken box thing, which kept breaking the boat because we broke the keel, the handle, the nose, a lot of different parts. So we worked on a box, and it was good. And you can see it just there. Oh, just there in that picture there coming off the plane, which was great. And the new stand as well, because the other stand was, again, broken. So yeah, thanks for listening. And if anybody does want to join us, you can go to that link there and enter your Aberystwyth email address, and we'll get back to you soon. Thank you.
Okay. Next up, we have Nathan. It's not working. Are you nearly working? Yeah, there's a microphone. So the microphone open.
No, no one can hear my voice.
Yes. Yeah.
Hi, anyone who doesn't know me, I'm Nathan. I'm on a IY at the minute at the NPPC, which is a big plant phenomics center where Colin works as well. So it's something positive. These things don't load cells, but really it's why you can't always use software to fix your problems, which is using so one of the things I'm working on at the minute is trying to get this thing called a gravimetric system to work. And it's essentially a fancy way of saying, let's weigh about a bunch of plants and water them every day and see what happens. But in a greenhouse, you have a lot of different conditions that doesn't make it easy to do that. Things like temperature changes, humidity, that sort of thing. Sensors don't really like that. So that's one of the big problems. Yeah, so we're trying to find a way to pretty much make it cost effective to do these sorts of experiments on plants. Just real basic introduction of load cells, for anyone who doesn't know. They're pretty much two little pieces of wire between two sensors, and you measure the resistance between them to work out how much something weighs. You don't really know what's going on that because I don't really know what's going on that. But they do keep me awake at night because of these sorts of things. This graph looks a bit complicated, but if you look at the top three sort of bars, that is, if you take a load cell, so a scale, and you set a 2 kilogram weight on it and leave it for a week, this is what happens. If you're trying to do this with plants that grow every day and get watered every day, it doesn't make for good science. This is one of the things I noticed I've been trying to fix for the last 3 months, I think. I was trying to just look at software solutions because I'm a software engineer, I'm not a hardware person, and I don't think there really is a simple solution to it. If you know one, please tell me. So I sort of wrote this atomic off XKCD because I thought it was relevant. Because if you look at these graphs again, there's no clear, consistent deviation between all three individual balances. You can see that the one at the very bottom is the multiplier on top of each other. So it's really hard to find a method that would link them up and say, correct for why they're wrong. Because they're all slightly different. There's no one quick fix for them all. So something that I always think about is how I can get around this. And unfortunately, the software is not the solution, it's a hardware problem. So I started building things that will get around the problem. Pretty much my current idea is let's take the plants away from the load cells. So I've been putting together little demos that look a bit like this. They look very shaky and scary, and that's held together with blue tack on my desk. It's got 4 kilos on it, which I'm really happy with because they kept falling over. And that work. The general idea is you put a plant on it, you lift it off again from there, and you can remotely tear your steels, and you hopefully get more accurate results because you're not constantly compressing a load cell. This is actually working on a 500-gram weight. Can't really see the screen very well, so I tried to put a magenta around it because everyone loves that. So one of the things I'm playing with at the minute is electrical linear actuators, which sound really cool, and they work a bit like stepper motors. Well, essentially are stepper motors. But if you want to lift something really heavy, like I want to lift about 10 kilos of plant at the minute per one, it gets very, very expensive, and they like to fall over. So the better idea I'm working on at the minute is using pneumatics to lift things, which is really cool because it makes a really cool like Star Trek door opening sound. That's my main reason for liking them really. But they're way cheaper than electrical actuators. At the minute, I'm trying to find someone who will lend me a big pump to essentially work them. So I don't want to run really long cable. Can you? That would be amazing. Okay, problem sorted then. That's pretty much it. That's my little rant. If you want to listen to me talk more about why load cells are really crap, you can check out my website. I think I have 2 or 3 blog posts at the minute on why load cells are horrible. That's pretty much it. Thanks.
Next up, we're going to have Mark, who's not in the program because I'm rubbish.
And because I have finance organisation skills.
Do you have any slides or anything? Excellent. Yes.
Wants to sell?
I can talk about myself.
Hey. Oh, that's weird.
Yeah.
Yeah. Oh, well, technology can't deal with it. Okay, so this fits really neatly with what I think we should talk about, because it's agriculture and plants and things. So I've got lots of slides here. I'll come to you really fast. This was kind of adapted from another talk. So. Basically, Tom Blanchard, who's not here, I was hoping he would be, he's not, did for his PhD a system which was looking at measuring climates on a really small scale. So looking at microclimates, how plants grow and why they grow when they grow in particular places, why they grow in particular sizes and particular shapes and that kind of thing. And the really interesting for that would be things like temperature and humidity and stuff like that. And I'll talk a bit more about what sensors use in a minute. During his PhD, for quite a long period of time in my field around my house, over about 500 meters wide. And it kind of grew out of that, and we've got a project that we're doing at the moment, which has extended this to a whole bunch of other things, which I'll talk about in a minute, which is where Zambia comes in and Chris can do it. So what we're trying to do is to make really cheap things that measure the climate at lots of places. And we'd like it to be practical in lots of different places, like in an agricultural setting in fields or around the edges of fields, in greenhouses, and out in remote places like Greenland and other interesting places that environmental scientists are interested in monitoring for long periods of time and ongoing that. So hardware. I love hardware. I shouldn't, because I'm supposed to be a computer scientist. I've been told off about this for many years by various different heads of department. I don't think Chris told me off much. Frank did. But there's never been more choice. Hardware's just amazing. The way it's changed over the last decade or two is incredible. Because it was always, you could get these really tiny little microcontrollers that were a real pain in the backside to use for anything and required you to have 25 years of knowledge before you could make an LED come on. And at the other end of the spectrum, you had a full PC, and there was almost nothing in the middle. And that's really, really changed. Since mobile phones came along and embedded electronics in dishwashers and washing machines and cars and microwave ovens and that kind of thing, it's just meant that there's a demand for all these intermediate scale devices. So you can pick how much computing you want, how many inputs and outputs you want, what you're able to do. You can pick anywhere on the scale, and that's fantastic for people like me who like practicing around with stuff. So we decided after going through various options with Tom that we'd do some stuff in this area, and he played around with various off-the-shelf. Well, there's a picture of my field, so that's about the red bit's about 500 meters wide. He built a network in here using XBs that some of you may have come across if you've been through a or whatever, with your blue things that have radio communications on them. He built a little network with those that sent data around about light levels and temperature and humidity and that kind of thing. And these things were, I didn't read with me, it's out in the foyer. These things were kind of aluminium box about this big with a solar panel on the front, all the sensors inside, and you drove a scaffold tube into the ground, and then you bolted this thing on the top, and you had a radio antenna coming out, and every time a buzzard sat on it, A, they cracked on the solar panel, B, if you didn't bolt it up really tight, it would rotate round, and the solar panel would no longer be facing south, which was suboptimal if you want to charge the battery, and C, they would eat the antenna. We lost about 50 antennas over the space of about 6 months. They would just get in there and literally tear off the plastic piece. animals are a pain in the backside. But it was fun. So just to kind of make a little bit of software in here. So it was all about, and the reason we did this deployment was about looking at how you could manage power in these sorts of systems. I'm interested in managing power in a whole range of systems, and these are quite nice because they're really cheap, really low cost. You can plug them out in the field, you don't really care if they get nicked. Actually, it didn't, because my house is so much neater than it goes there. You don't mind if they break, and if the buzzer needs to go on antenna, that's okay, because it's 10 quid to buy another one, 5 quid to buy another one, whatever it might be. What we were interested in doing was looking at how you could then make the most of what little bit of power you did get from your solar panel. And these ones had 6-watt solar panels, which are pretty big, about this big. And the system he built was almost, well, it was deliberately suboptimal in terms of power consumption, because then that gave us a range of options to play with. So we could ramp things up and ramp things down, and we could build a control system that would make it run out of battery. And we could build other control systems and control them in different ways that would allow us to test different regimes for controlling how much activity these things did, how much measuring they did, how often they came on, how much data they forwarded through the network, and that kind of thing. So it was kind of good fun. We did that for a while, and he came up with this. Well, we've been playing around with this analogy with hormones for a long time. He came up with the selfish hormone, and I'll show you a couple of graphs if you have to. They're probably a bit more meaningless than these graphs were. I understood these graphs. Basically, things that go really low are bad. Okay, so the green line that dips right down to the bottom there is bad. Each little blip, this is battery voltage on one of the nodes. Okay, each little blip is a day. So when the sun comes out, the battery voltage climbs up a little bit, and then overnight it drops down again. Then the next morning it climbs up and you get down. So each blip is a day. So after about a week, here, one of our nodes has dropped down to 3.5 volts, which for a 6-volt lead acid battery is death. Okay, so that node's effectively died. And this was just using a simple regime where it was on for 500 milliseconds. I had a 500 millisecond time cycle. It was on for a few milliseconds of that, and then off the rest of the time. So it cycling itself around. And this was so that each node could forward data from other nodes. They're transmitting data to each other with radio. So if you want to be able to do that effectively, you have to be on for a while every now and again to be able to hear other people transmitting. Because when you're asleep, you can't do anything. Okay, so if you want to save more power, you have to be more antisocial. You have to be selfish. You turn yourself off for longer periods in order to conserve your battery. So this was a control experiment where it was just on for fixed periods in that 500 millisecond sequence of events over time. And this was over a couple of weeks. And you see, by the end of it, I think 2 or 3 of the nodes had killed themselves essentially and actually trashed the batteries. The batteries were useless after this experiment. So using his little algorithm, he came up with a way of basically, as the battery voltage dropped, so there was less power available, the sun wasn't out so much, you would ramp down the amount of time you spent on, and therefore you would save a little bit of energy. You would also then forward fewer packets from your mates. The other nodes in the network would not be able to send their data back. They try and send you things and you weren't awake as often. So they would fail to send so much data through. So you get a little bit less data, but at least everything pretty much stayed alive. So after a couple of weeks, we had one node that went off for 6 or 7 hours, and then when the sun came out the following morning, it charged again. And they basically lasted for about a month before we had lots of nodes dropping out. And this was actually later in the year. This was in about November, so by this point, the weather was really rubbish. There was a lot of sunlight around. So we could make quite a difference. That's kind of why we got into this area, was to look at how we could manage power on these sorts of devices where you have fixed, an uncontrollable amount of energy coming in. There's nothing you can do about the amount of energy you've got coming in. You've just got to decide how you're going to use it the best. And you want to maximize the amount of data you get out and maximize the lifespan of your device. These things in the field and they just work forever. It's not going to be like that because we have buzzers and stuff like that. Okay, so that was an XP-based system, and it was big and it was chunky and it was really quite expensive. They were just the electronics ended up being about 90 or 100 pounds, I think. So we then moved to Arduino-based things, and quite a lot of you have probably come across Arduinos. And there's a little thing called a Motino, which is an Arduino version which has a radio built in, a low-power radio built in, 43 megahertz radio, which is one of the open, free-to-access wavelengths that you can use in the UK. You get about 500 meters out of them if you've got a good clear line of sight. If you do a bit of tweaking and you mess around with things in non-standard configurations, you can get a little bit more than that, especially if you dial up power settings to things that might not be legal in the UK. But of course, we never do that. It's really, really easy to get going with. So if you're interested in doing kind of Internet of Things stuff or radio-based stuff, they're about 12 quid, I think, for a Motino, which is an Arduino-compatible thing. You need an FTDI cable. You get a special cable to program it with, but you can program it from the Arduino environment, and you get a radio module, some nice libraries, and you can get communications going. If you buy them, you take them out of the box, you plug them in, you get communications going within about 5 minutes. getting going. So they're really quick, really easy, fairly long range, really cheap. I've got loads of projects that I'm using this for now. They're kind of my go-to toy at the moment because they're fun. You can do addressing and packet filtering and all that kind of thing in the hardware. It gets a bit more complicated if you try and do that kind of stuff, but you can do it, and that can be really useful. The only thing they don't have is they don't have any routing and meshing built in. So if you have a network of these things, you have to decide what route the message takes through your network. You have all these things scattered around your field, and you've got something in the corner over there that wants to communicate with your base station. You have to decide for yourself in your program how it gets through the network, what route it's going to take, and who forwards things, and that kind of stuff. Which is good fun, but if you're trying to do stuff like we are, it gets a bit irritating. So it'd be quite nice if there was a library to do that, and Tom may be working on one. Whether he'll get it working or not, I don't know. Okay, and they're fairly low power as well, as you work down in mind, so we can get away with a much smaller solar panel, like this one here, which is a 1 watt solar panel, instead of the 6 watt one that we had on the other ones. So, yeah, we wanted to get rid of the box, because the box was just a bit irritating. It was a real pain to deploy, because you ended up with a rucksack full of aluminium boxes, walking up and down hills with 6-volt lead acid batteries in them. You got very tired very quickly, and we also damaged quite a lot of them carrying them around, because they're big and chunky. Because if they're big and chunky and heavy, you're tempted to put as many as you can in, so you end up counting loads of them in, and they sit on top of each other, and you scratch solar panels and break even more antennas and stuff like that. So we tried to think, how can we redesign this? And the thing that I came up with, and Tom hates it, but I quite like it, so I think it's fairly simple. We still use a scaffold tube that we drive into the ground, but now we put all the electronics in line with the scaffold tube. My original design, the electronics actually went inside the scaffold tube, hung down from a cap that sat on the top. Yeah, you can't really see it, but on that picture there's a scaffold tube driven into the ground. That's the great thing is the little blue bit on the top you can just about see. There's a little plastic cap, and all the electronics and batteries and stuff are hanging down from that inside the post with batteries and everything built in. And there's a little tiny kind of black speck that you can see about a fifth of the way down the pole, which is the solar panel, on a little bracket sticking out the side. And the white blobs poking out are where the sensors come out. So we have one sensor at 1 meter above ground level, one at 20 centimeters above ground, one at ground level, and then we have some sensors underneath the soil as well. The sensors that we use are really cheap. So these little, you can see from the bottom way, these little white things, they look a bit like sort of waffles. These are our temperature and humidity sensors. They're about £3, and they're amazingly reliable. We've had a couple hundred of these out in the field down in Berkshire, and touch wood, I think we've had one fail so far, and I think that's probably a cabling problem that I introduced by not being properly on it. And we have variable temperature sensors, which are these things that you can buy from Adafruit or various other places online. And we've had a lot of problems with stuff that you bury, because you buy things that are marked soil temperature and humidity sensor from someone like Adafruit. You bury them in the soil, they work fantastically for about 3 months. And then you dig them up and wonder why they're not working, and then you take them apart and you realise that all the stuff that you thought was waterproof isn't waterproof. It's all gone green and corroded and died and stuff like that. So we've been experimenting with some new sensors, and this thing is a thing called a Vegetronics. It comes from a company called Vegetronics. This is to measure soil moisture content. Quite clever. Normally you just have 2 probes and you measure conductivity, so how much electricity flows through the soil, and that depends on how much water is in the soil. Obviously, the more water you put in, the better it gets. This doesn't. This is inductive, different thing. Technology, it's fantastic. Has been dirty books taken too long. Base station is a dirty, great big scaffold construction. It's 2 meters square and an antenna 3 meters high, and yeah, whatever. It's got a GSM modem in it, which connects to the internet via the phone network. Solar panels keep stuff going. Raspberry Pi, Martino, all this stuff, and that channels the data from these things back to the network. That's it. So, if you're interested in having a look, or you want to get involved with Martino stuff, or you want to play with things, come talk to me. I have lots of fun kit flying around, and come and see you about compressor. And we'll give you Thank you.
We'll keep going on through the talks because we've got to be out of here at some point. It's all right. It's all right. Can I use your laptop afterwards? You've got a web browser on it? Cool. That's all I need. Yes. Yes.
Yes. Okay. Quick question. Can you guys see that text? Or is it super small?
It's very small though.
Very super small. Okay.
No text.
Yeah, try and yeah. We'll put that in the comments. Is that better?
Still small. It's bigger, but it's still small.
Okay. I'll try it a little bit. Okay, hi guys. Before I start, quick question. The little poll on text editors and things. I think as a programmer, it's very important to be curious about them. What do people use? I'm curious. Do people use Sublime? 1, 2. Atom? Yeah. Eclipse? IntelliJ? Vim?
Yes!
Oh my god, people do actually use Vim. That is great. Emacs? Oh, it's not you actually. Okay, so it's a pretty mixed group. I think this talk hopefully will interest some of you. Anyway, so this talk came about basically because as a student, all the projects I've been doing focused on maybe 10 different files I was editing at once. And then I went away last year for an industrial year, and all of a sudden, 10 files went to hundreds of thousands, and it was kind of scary. So scaling up your favorite editor to be able to handle dealing with that many files was a bit of a panic. And one thing that I'd always been put off is using plugins, because the thought of if you get everything set up on your machine exactly how you like it, and then you have to work on another machine or another server, it's a pain. You've got to set everything back up, you've got to install your plugins, and I don't really want to do that. However, thankfully, there is a solution. I have set it up. So this is stock Vim. I have nothing installed. I've applied for RC. But what I have been able to do is if I pull down my Vim RC from GitHub and save it onto my machine, if I now launch Vim, it will, after a few errors, it will go and install all of my plugins, my theme, it'll set up undo directories, it'll do absolutely everything. And then on second launch, it will actually even compile a few extra things. So now I have this set up exactly how I like it, and everything is brilliant. It makes life so much easier. You can go to a new server and just instantly you have your setup as you want it. Very useful. I know at work a lot of Sublime users, if they ended up pouring water on them backwards, which happened quite a lot, their Sublime configs were lost and it was okay. So plugins are actually pretty great. If you can do it like that, you don't have to spend time setting them up. So one thing I'd like to talk about that is hopefully interesting to the new people and to the experienced Vim users is the idea of composability. So the way that Vim differs from your average editor is that it's aimed at editing. It's not aimed at entering text, it's aimed at editing text, which if you're a programmer or a journalist or someone that writes a lot, that is what you're doing a lot of the time. You know, it's rare that you're writing a whole source file from scratch. So the idea is we get verbs, motions, and text objects, and then we can compose them together in a language so that we can use them. So you learn one set of verbs, and then you can apply it to everything. So the verbs we have, for example, are delete, yank, and change. So that is delete something or cut it, copy something or change something. And change is basically deleting and going into insert mode. Motions, these are things that allow us to jump around the document. So ends of words, beginning of words, from a word, that sort of thing. And text objects are objects in the text that you learn to pick up, and then you can use those to navigate as well. So I'll give you a couple of examples. So DIW allows us to delete in a word. So if I go in and we have a few words here, if I want to delete this word, I can do delete in word. Okay. But now, if I want to yank in that word, what would you think I do? It's pretty simple. Yank in word. So now I can do yank in word, and I've got that open, so I can then paste it. Okay. Actually, let me open up some source. I can see my screen, which is good. Helpful. Okay. So this is so if we want to apply one of these motions to, or apply one of these verbs to a different selection. So if, for example, we want to change what's in those brackets, at the line. Okay, so we want to change what's in there. So we can do change in brackets, and now I can put whatever I want in there. But then if I don't want to change what's in brackets, I just want to change what's in the quote marks, I can change in the quote marks. So you get the idea. You take one option, and then you apply it to that motion, and then you can apply that to everything. So in learning these few shortcuts, I've learned, I haven't done maths, but loads and loads of different combinations. So you've been able to, instead of Control-C for copy and Control-V for paste, you learn Control-C for something in a bracket, in a quote marks, in a sentence, in a paragraph, etc. And then you can apply all these different kinds of verbs to everything else. So if, for example, I want to comment out this paragraph, which in this is a block of text separated by lines, I can do comment out in paragraph. Comment out a paragraph. If I want to do, I think of examples, but so yeah, so that's it. You can stick things together. Other things that have been very helpful when managing lots of files is some of the excellent plugins. So there's a tree, if people like a tree, which most do, which is very handy. You have fuzzy file finding, etc. And then the best one for me is Git. So you can Git blame things. It wasn't me, I promise. And then something that is invaluable if you're working with a team of people. Select a line and browse that line. So if you want to send a link to someone to say, oh, that line, there's something on there, I can really easily generate that link and send it to you. There's also things like Google, so I can Google what a word means or what a selection means, and pasting things so I can paste that. All little helpers which make life a little bit easier. The other thing that I found fascinating is learning more of these text objects. There are loads built in, probably more than I've even bothered to learn, but you can always add more. So one that's very handy is indentation. So if you want to operate on this indented block, there currently isn't really a nice, easy way to do that. However, one of the plugins will allow you to do that, which is change the indent, or delete an indent, or yank indent, whatever you want. You can always add to it. Another one is arguments. Is this? Yeah. So this is very much in arguments. Changing arguments. Yeah. So it takes everything before the comma. And then things like in between the dots, you can change in dot, and that'll take that. So if you take this concept of composability and you extend it to all of these extra things, it gets really, really powerful. How am I doing for time?
Done?
Yeah, right. Didn't really embarrass so much. Cool. All right. Well, I hope that's given you some insight into what Boot can do. Any questions? I'll try that. No, I get RSI. Cool. Thank you.
Mode. Okay, that was Vim. And now I'm going to do a quick talk about crap VR. bit.ly/crap_VR. Okay, and I'm basing this on kind of on a talk I went to see at Electromagnetic Field Hacker Camp in the summer, which was called Imperfect VR. But once it got into my hands, it became crap VR. So there you go. And if anybody wants to have a go, we've got some headsets here, and you can check these out on the headsets. And I've got some headsets for sale as well. The basic idea is that in order to do VR, you no longer need to have like a HTC Vive. Obviously, it's not as good as having a HTC Vive because like, the Vive is really cool, but actually, you can do quite a lot of VR stuff without doing any major coding at all. So, this is sort of lo-fi virtual reality. I don't know if anyone's come across the Gartner hype cycle. Hands up if you've seen the Gartner hype cycle. Okay? So the idea is you've got this cycle of technology, and it goes from the innovation trigger, which has things like neuromorphic hardware and volumetric displays and quantum computing is there somewhere, obviously, every time. And it goes up to the peak of inflated expectations, down to the trough of disillusionment, and then the slope of enlightenment, which is where things start to become productive. And Gartner releases every now and then. And this is the most recent one, the 2016 one. And virtual reality is finally on the slope of enlightenment. So I'm taking you to the slope of enlightenment. But there's been a lot of hype. I mean, if you look at virtual reality, you see images like this, yeah, which are just fantastic, show you the potential of VR and what VR can bring you. And it's just something else, right? But actually, you don't need these 600 quid headsets. You can do it with a bit of. That's actually not got a phone, so it doesn't work. Actually, that's not got a phone in either, because I was using a phone to take something. Completely faked. So what if you think about what you actually need to have to do VR, there's a couple of things that sort of ingredients. You need 3D, so you need to be able to move around in 3D space. You need some kind of stereo, so you need to be able to present different things to different eyes. And you need some kind of head tracking, so that the world moves as you move your head. And actually what we've got is all of that now exists in browsers in your phone, because the browser in your phone can access the accelerometer, so it can tell what angle the phone's at. The stereo, you can just flip the screen. 3D, you've got WebGL. So your phone browser can now do proper VR. Well, crap VR. So, yeah, that's basically what I said. So you can also get 3D cameras. I've got one to show afterwards if people are interested. For under 300 quid to do 3D capture as a sphere. You can do photospheres just by stitching the phone together. You get 3D models from places like Clara.io or SketchUp. And people who are doing 3D printing can also know a lot about getting 3D models from different places. But it's not very good. I hear you cry. If you've tried it, you realise it's not the full HTC Vive experience. You do not feel like you're on a different planet. But one of the quotes that came up at this workshop over the summer that really moved me. All perfect art is reactionary. Embrace the imperfections in what you're doing. Yeah? Embrace the glitch. If you look at my 3D things, you can actually sit in a glitchy 3D photosphere of this very room. And I can tell you there's nothing stranger than being in a virtual version of a room that you're actually in physically. And you can find beauty where you can. You can find things that you would not maybe otherwise think of as beautiful. But anyway, enough of this. Take me to the couch. The way we do this is something called aframe.js, which comes from Mozilla's WebVR team. It sits on top of 3.js. If anyone's ever tried doing WebGL, you know that 3.js simplifies WebGL a lot, and A-Frame simplifies 3.js. So if you're used to doing WebGL, it's kind of like programming with boxing gloves on. But if you're not used to doing WebGL or you don't like WebGL, which is the camp I sit in, it's quite nice to be simplified. So you've got a lot of the geometry is dealt with for you. It gives you lighting, it gives you photospheres, images as textures, 3D models so that you can import 3D video, and all sorts of geometric primitives. You include the library, which is just a standard script include, and then you're good to go. So this is all of the code you need to do a VR photosphere in WebJS. A-Frame.js, so you set up a scene. In that scene, you identify some assets, so there's the image, which is perhaps a picture of B23, and then you say, I'm going to set that as my sky, and there you go. Everything else is handled. You can look around, you can see that is exactly the code. You can give yourself a viewpoint, which is a camera, obviously with a 3D world from a particular perspective, so you can move the perspective around. There's certain primitives you can use, so spheres, boxes, and so on. And looks like this.
It opened already.
It looks like this, which is there, it's there, I tell you it's there, behind you. So this is, looks like in the browser to have a look at it. If you go to bit.ly /crap_VR, there's all sorts of cool examples there. Not that cool, actually, they're all made by me. I made a game where you move around avarice with the most horrible paths. So I think that might be, you might have just seen it, I'm not the only person who's ever taken photos of the vineyard at the back of the map, but you could be there in virtual world. And A-Frame.io is the site, and they've got some really cool demos. Video, all of these are just done in the technology stuff. So pretty much everything I've shown you, apart from the game, you just got a little bit of programming JavaScript, everything is just declarative. You just say it's there, and it works. And that's that. And that's me. So, next, Kieran. Kieran. You can. I'm sure I reminded it. Okay, I reminded it. It's a bit. So, Kieran's talk title is "Can dogs diagnose lung cancer?" Yeah.
Sorry.
Good.
Talk now.
Detect. Sorry, not diagnose.
No.
Detect.
Okay, can everybody hear me, first of all? Yeah. I do have a tendency of speaking way too fast, so if I do, someone just put a hand slow down. Right, so my name is Kieran O'Shea, and I'm a second-year PhD student now. I'm working with IBAs and computer science, so I'm trying to develop the high-throughput, cost-effective way of detecting lung cancer. So we've all probably read in the news over the last few years that dogs can supposedly smell lung cancer. A bunch of researchers in Germany who were probably bored tried to use dogs to actually diagnose lung cancer and ended up with around 72% accuracy, which is actually much higher than clinicians within the UK. So to really kind of understand, how the dogs can actually do this, you have to first understand the nature of the disease. So unfortunately, we've got to talk a little bit about lung cancer. Horrible disease you guys probably know, and it's categorized into two main types. So you got non-small cell lung cancer and small cell lung cancer. The other one. It kills around 1.3 million people every single year. Cancers in general cancer care, cancer treatment, etc., etc. It has seen very, very little improvement over the 5-year survival rate, and this is due to the fact that it's extremely difficult to diagnose. And I was a bit, down, so here's some pictures of dogs. So, of course, as we don't really have that strong sense of smell like dogs have. So, but what we do have are expensive machinery. So, this is just a quick introduction to a field of biology. So, Basically, to do this, we're going to employ metabolomics. So this is the large-scale study of small molecules known as metabolites. And these are the small molecules found in cells, in biofluids, in tissues, and in any living or dead organism. Metabolome is basically the combination of these metabolites that's produced or to inhibit a small biological system. And unlike other omics approaches, it gives us the underlying biochemical activity at the time of sampling, which means that when you take the sample, what you see is what you get at the time of sampling. It's also incredibly cheap to perform. So when I first came here, samples were being taken down in Princeton Hospital in Connecticut. From this, we were able to take 33 healthy controls, so healthy beings that smoke quite strong, quite heavily, have COPD, or just generally unfit, so the kind of people that would normally come in to a GP to say that, oh, I think I might have something wrong with me. We're also able to take 23 sputum samples, so phlegm samples from people with lung cancer. These samples were then prepared, first frozen, and then it was spun using a vortex mixer, centrifuge, and a pellet was removed, and the pellet's about the size of my little fingernail. This was then put into a mass spec machine where I used where FIEMS was used to take matrices, basically showing the weights, etc., of each chemical compound within that sample. And from that, then I did the computer stuff that you guys are interested in. So further analysis using statistical univariate analysis and neural networks, etc. And of course, using Facebook on the board. And from this paper was published, where we were actually able to diagnose lung cancer against control with around 90% accuracy, which was quite nice. And we were also able to take these 5 identified metabolites. But on further inspection, something interesting happened. So in these boxing whiskers charts, you have your normal things actually causing cancer, like glycines, glucose, which is sugars, etc. But if you look in the top left-hand corner, you have this thing, I can't pronounce practice today, the citric acid. So this is actually quite an interesting chemical. It has quite a distinctive smell. I smelled it myself. I'd say it smells like honey, and so would around 50% people. But others also say that it smells like copper. It's classically associated with PP, I can't pronounce that with modern copper, which is a sort of immunometabolism, which basically allows toxins within the biological system to develop any fight back, and it's potentially lethal, especially in children. And with just this one metabolite, we were able to actually classify whether or not the sample had lung cancer or not with 92% accuracy. And for the statisticians, it's significantly significant. And we also found that it was actually higher in cases of small cell lung cancer. Now, I'm not a biologist, I'm a computer scientist, but my supervisor told me this is probably because it causes inflammatory events that occur within the lung, which of course reduces the ability to deal with the disease at the earliest stage, which of course could then develop into the nastier form of small cell lung cancer. So I don't know if the myth has been confirmed yet, but there's obvious signs that there are metabolites within sputum samples and within saliva samples which do smell differently than normal. So maybe that's what dogs are picking up. So we all know that at the moment we have massive problems within the NHS. We have to make massive cuts. So I've come up with a 3-step plan to say it. So first of all, we're going to sack all of our clinically trained doctors. There's no need for them anymore. You know, this obviously proves it. We're then going to replace them with dogs. That would be cute, but because people don't want every dog next to them on their sick bed. And we can all sit back and we can all relax, knowing that the NHS is safe for the time being. Thank you for listening.
Brilliant. Right. That's our last, second to last talk. We got one last more to come. Passing around. Yes. And Ariel. And Ariel. Yeah. And Ariel. Sorry. Cool. Yeah. Sure. Is that right? Yes. Back to Ariel. Oh, I've walked off with the microphone. Okay, well done everyone for sitting through all of this. It's supposed to be more breaking up, but the pizza arrived 45 minutes early, as you probably remember. So, over to Plastic.
Hi everyone, I'd like to apologise first I really bad voice expressions. Yeah. And also not feeling too well. But yeah, I'm going to talk to you about my first year of university. Now, I understand which was not really into computers and tech and stuff. I am as well. And I'm studying artificial intelligence and robotics here at ABBA. But I want to talk about a bit of a sidestep. Now, we all get degrees for different reasons. And believe it or not, I'm not actually a big coding fan, nor am I a very good programmer, but I do try. So I came to get a degree so that I could maybe do my job better. So about a few years ago, about maybe 6 years ago, I filed a patent. This patent was something called the Sky. It was for an invisible road network in the sky, which drones were able to navigate from point A to point B. What we're supposed to do is very simply, someone buys something online, very similar to Amazon's drones, before Amazon's drones. It was simply that road network in the sky. I lost faith in this idea, realizing that a bit of snow, Gatwick Airport shuts down. And I thought, if you've got a million packages you're trying to deliver, it might not happen, or it might not be a very sort of viable commercial option. Then I had the idea of cars. Maybe we could build a vehicle. You buy something online, and after you've bought something online, a driverless vehicle would automatically drive down the street, pull up in your driveway, and get your package. It could call you. There'll be an app to come with it. That's a solution I went for. Now, I have experience in building teams of people to be able to do this, but I didn't feel that it was fair for me to try and do this without any knowledge at all. So I thought I could cheat. I'll come to university, I'll learn how this could be done, but then I'll do it on a smaller scale first. And then came the birth of something called you. Now, many of you may not know, I devised a library robot idea that we were going to have this robot which would be able to navigate your own library and take you to any book. The ulterior motive was, it was essentially my sort of crash course in robotics and how this could be done. So a few students and I got together and started designing what this robot could look like. Now, to tell you a bit more about you, which is quite relevant to this talk, I'm going to call over.
Okay, so this is the point where I get to like run and plug Hugh for a couple of minutes maybe. We didn't get a separate time clock for it, but basically Hugh is, as Will mentioned, a library robot helping you essentially find the books. Books all have class marks, and it's not really easy to actually figure out where the books are located in the library. So it's a good essentially excuse to come up with a project where we could make a robot that not only sort of figures out resources located in a library floor, but also allows you to be guided by it. Right? So we both get a bit of hardware and a bit of software. So essentially, we're at a point now where we have a prototype for the robot itself, and it looks like ET. I like that for the time being. At the moment, that's in customs in Norway, because I had it in Norway with me over summer to sort of lead through the house and a bit of that. So no show part, but the tell part is that we want this to be something that can wait for you in the library floor and essentially help you around. So the cool thing about this project is that we have quite a few different modules. I'm mainly here to sort of hope to recruit a couple of you to come and join us, because we have both sort of hardware aspects of this and software aspects of this. Lately, I've been working up against the API for Alma, or Primo as we know it, to sort of retrieve information on the books and such. And that's going to be its own module when it all comes down to it. And we also have the voice integration and the sort of more aspect of it that uses ROS, the robotic operating system, essentially power the base around. As some of you may have noticed, the base we use now is a Kabuki, really nice sort of easy to get set up base, but we wanted to transition to something that's more sturdy and noise-free. Also, the Raspberry Pi here, that's from last September, from sort of courtesy of the BCS. I had a talk there and was fortunate enough to be aware of that. So it's been good to use. Anyway, one thing we've sort of encountered that's kind of interesting in is that there's always a bit of feature creep in these projects that are initially very sort of ambitious. We have quite a few different modules. We need to sort of string all this together. And along the way, we figured out that the library doesn't actually know where the books are. Those sort of lists here at the end of each bay or aisle, if you will, they're actually printed out by hand from a template. And every time the staff update these, they go in and look at what's actually in the shelf, and they update the class codes from this to that. And so when we sort of set out to help people find resources, we assumed that we could sort of hook into some backend. But it turns out that we have to make that backend. But it also turns out that the library is keen on us making that backend, because that would make their life easier. Because now suddenly they could have a way of knowing where everything is and just hit print for a selected bay if a resource is added or moved. And so a lot of the work that goes into sort of manually updating could just be automated. Now it's actually, of course, not trivial, but it's funny how, like, as you go along, things sort of just build. Anyway, we're at the point now where, again, stringing things together is the main priority. I've tinkered enough around in APIs and with sort of the mobile base and everything, where we want to have a prototype up and running as soon as possible, because we do realize that having something tangible is very much the key to gaining traction. If you look at Sailboat, for instance, there's a beautiful boat out front, and that is certainly something that sort of is very, very tangible. So next step for us is essentially just like getting to the point where we have something to show you guys that actually works. So yeah, back to you.
Thank you, Aya. So coming back to what I learned, as the start of this talk is actually what I learned, what I did my first year's knowledge. So some of you may recognize these little robots on the screen. This is actually Mark Neal's Arduino class, where we're taught to control these mobile robots. I think the class or the session at the time was we learned how to move them in a straight line, follow a path. It was quite basic. And then the other screen you see over there, just under the other folks see just underneath, are the Pioneer robots, which we worked on. I think it was Apalachi's and Elio's PhD. So Apalachi's PhD and Elio were part of the team working on those. Now, what's really interesting on the right-hand side is a screenshot from our Java project given by Chris Loftus. The relevance of this is these were, I think it was called bonks and zaps. Now, what bonks and zaps were these little beings that moved between rooms. This is what I did with it. What you see in front of you is a vehicle sort of prototype image, where above it is a package swapping mechanism, where essentially a vehicle drives, and as it's driving, it can swap a package swap packages between sort of the delivery. So from point A to point B, if that's a customer in this area or customer in that area, you'd literally be able to swap and pick a different package. So part of the process was I then spoke with the Department of Transport and got one of the first licenses to build a street legal driverless car, which is able to do the deliveries. I then started building a team, and let me show you this first. So to give you a better example, here's the car. We're going to hollow it out, and then as it's going to hollow, we're going to zoom in, and there you see Bonks and Zaps version 2.0 or package swapping. Here's a closer look. As you see, picks up a package, pulls it out, takes it out of the slot, and out it goes. And it can perform multiple deliveries at once. Okay. Sorry. So, my summer holiday. I spent my summer going to see venture capital. I think I visited 11 cities, saw from BP to Microsoft, everybody. The result was about £1 million in funding to start building these cars. And here you see me with an Atlas t-shirt filled with where we're building the cars. You might recognize that face. That's Dr. Elio Tichy, one of the former professors here. He's looking at, he's fascinated by the process. Now, I'm going to switch over and show you a quick video. Now, I apologize, this video is not, it's one of the sort of drafts we had for our marketing a while ago. Because I've just moved back into Avon, a lot of stuff is still missing. So I'm going to play this for you. Now, I don't know if sound come out here. So, possibly, this is a summary of our journey. Here you will see a picture. Actually, no, expect. So this is how the team, original team for Team Q actually, as we're working on the robot. I'll just take the video play and then questions after that. Originally a fundraising video, but this is carbon. And that's what I did my first year of university knowledge. Thank you very much, people. Well, I'm speechless. Anybody else raise $1 million of VT funding this summer? No? Well done, mate. Well done. But that's the end of the talks, I believe. So if there's anything left in the foyer that hasn't been taken by passing people, we can go back to the foyer and see if there's anything left. If anybody wants to ask any questions or distribute any stickers, that's good. If you remember the post-it notes which you were given at the beginning, give them to the person that did the best talk, and they might win a Raspberry Pi. Raspberry Pi starter kit worth slightly less than $1 million of VC funding. And we'll announce the winner in the foyer in maybe 10 minutes. Yeah, 10 minutes. So that's the end of the formal bit. We go back to the foyer. Anyone wants any VR glasses? I've got a whole box here.
In case anyone wants to hear what this thing would actually sound like, I'm going to start it running and it'll be new big and white. One of the
to find the guy to give him this, and you can't just write down the thing.